of traffic phenomena. And lastly, I'd like to show that longitudinal control model can replicate microscopic fundamental diagram and these traffic phenomena. All right, so let's get started. Traffic flow theory borrows ideas from fluid dynamics. There are many ways to observe, or measure the motion of a fluid. Take fluid in a channel, for example. Here, each fluid particle is exaggerated as a fish. One way to observe the motion of these particles is to put sensors at fixed locations and record the state of the particles passing these locations, such as the speed indicated by the green arrows. And this is called the Eulerian description. Well, another way of observation is to fix sensors to each particle and record the state of the particles as it moves, such as the speed indicated by the red arrows. And this is called the Lagrangian description. When studying the dynamic behavior of the fluid, the Eulerian description and the Lagrangian description can be related to each other using theorems such as fundamental principles of kinematics, material derivative, and Reynolds transport theorem, where the variables in red are based on Lagrangian description and variables in green are based on Eulerian description. However, sometimes our interest is not in the dynamic behavior, but rather the ensemble behavior of all particles over the long run. For example, the average speed of particles. One way to determine the average speed is to focus on a single particle and determine its average speed over time, which can be done based on the Lagrangian description, see the red bar. Another way is to take the average speed over all particles at the same point of time, which can be done based on the Eulerian description, see the green bar. A system or process is called ergodic if the time average of a single member over a long time is equal to the ensemble behavior of many particles and many members at a fixed time. Similarly, in traffic flow, mobile sensors, such as onboard GPS devices, provides a Lagrangian description of traffic flow, while point sensors, such as loop detectors, video cameras, and space sensors, such as helicopters with cameras, provide Eulerian description. Lagrangian description provided by onboard GPS devices can be represented as vehicle trajectories in the time-space diagram. Eulerian description provided by a loop detector can be represented by a horizontal line crossing vehicle trajectories, while Eulerian description provided by helicopters can be represented by a vertical line crossing vehicle trajectories. Fundamental diagram is an Eulerian description of ensemble behavior of traffic flow based on observation by point sensors. Though the general trend of the data cloud indicates the statistical relationship among flow, speed, and density, it is not convenient to use the data cloud to help with the traffic analysis and control. Thus, there comes the need to have some models, such as green shields, to represent the data cloud, which are more friendly to use. These models are called equilibrium models because they use functional forms to represent the equilibrium states of flow, speed, and density. For example, when the states are disturbed and driven away from their equilibrium positions, there's a natural tendency to return to equilibrium without external involvement, like the mass spring system. If traffic system is ergodic, its ensemble behavior can be started from the individual vehicle over time. This example shows the dynamics of the red car following the blue car in front and plots their speeds and spacing over time. The time development of vehicle motion dynamics can also be represented in the form of a fundamental diagram where speed-spacing relationship is generated directly from vehicle motion dynamics. With this result, the speed-density relationship can be obtained since density is the reciprocal of spacing. Building on which, the flow-density relationship and speed-flow relationship can be derived by using the identity flow equals to speed times density. Since this fundamental diagram is obtained from microscopic vehicle motion data, we shall call it the microscopic fundamental diagram. To avoid confusion, we shall call the regular fundamental diagram generated from traffic flow data the conventional fundamental diagram. In addition, there's a macroscopic fundamental diagram which applies to urban neighborhoods relating number of vehicles to average speed. Note that our discussion here focuses only on micro and conventional fundamental diagram. To facilitate the discussion, we plot a microscopic fundamental diagram on top of the conventional fundamental diagram, just to show how they relate to each other. As discussed previously, the ensemble behavior of traffic flow can be studied from the perspective of Eulerian description, which is the conventional fundamental diagram, as well as from the perspective of Lagrangian description, which is the microscopic fundamental diagram. The ergodicity property of traffic flow implies that both fundamental diagrams are equivalent, which describes the same object just from different perspectives. The primary use of conventional fundamental diagram is to inspire equilibrium models, which fit the data cloud using functional relationships between speed and density. The resultant equilibrium models are useful in many ways. For example, traffic flow modeling based on LWR model, which is this part, including graphical and numerical solutions, highway capacity and level of service analysis, and traffic control such as ramp metering. Except for that, conventional fundamental diagram appears more like a mystery to us. It raises more questions than suggesting solutions. As a result, conventional fundamental diagram alone appears inadequate to help us understand traffic flow. The limitations of conventional fundamental diagram are identified in terms of regime coverage, cause and effect, cloud distribution, and feature highlighting, as will be explained as follows. Regime coverage. A point sensor may not be able to capture some states of traffic if kinematic waves representing these states do not sweep through the sensor. As a result, some portion of the fundamental diagram may not manifest themselves. This is particularly true at locations where lanes are managed to purposely avoid congestion. Thus, field observation over a long time, typically months or years, is typically expected in order to reveal the full picture of conventional fundamental diagram, but there's no guarantee. In contrast, a mobile sensor, such as a GPS device, is more likely to capture different states of vehicle dynamics, since the vehicle is more likely to experience these states as it moves in the traffic. This means The skeleton of a microscopic fundamental diagram can be easily sketched out by a vehicle running for a short period of time, such as typically in minutes or hours. As a matter of fact, we shall see later on that it suffices to replicate a microscopic fundamental diagram by simulating car following in just 5 minutes. Cause and effect. Conventional fundamental diagram only shows the statistical relationship among flow, speed, and density without suggesting the cause-effect relationship behind. Of course, the fitting of the equilibrium models appear to suggest that the speed-density relationship is the cause, while the derived speed-flow and flow-density relationships are effects. As a matter of fact, from the microscopic fundamental diagram, we notice that the motion and dynamics of vehicles give rise to the speed-spacing relationship, which in turn results in the speed-density relationship, which further in turn leads to speed-flow and flow-density relationships. And therefore, among the 4 subplots of fundamental diagram, speed-flow and flow-density relationships are effects. Speed-density relationship appears to be the cause. But in a deeper sense, speed-spacing relationship constitutes the root cause, and behind the scene, the motion and dynamics of vehicles is the origin of everything. Cloud distribution. Conventional fundamental diagram shows a data cloud without giving a clue regarding the distribution of data cloud. For example, why there is a dot at a specific location, what happens behind that dot, why some locations have more dots than other locations, why some locations have no dot at all. In electrical engineering, when a signal is hard to analyze, engineers are used to transferring the signal from time domain to frequency domain to reveal hidden information. Similar technique can help in our case. When viewed from the perspective of microscopic fundamental diagram, answers to the above questions are easier to find. For example, each dot in the microscopic fundamental diagram can be traced back to a particular state of a vehicle and its relationship with the adjacent vehicles. The reason that some locations have more dots than other locations is because the dynamic states corresponding to these dots are more often captured by sensors than other states. Some locations have no dot at all because either the corresponding state is never captured, or such a state normally does not happen. For example, approaching a stopped vehicle at very high speed. Feature highlighting. The data cloud in conventional fundamental diagram appears as is, so viewers have no clue about the distortion of information behind. Looking from microscopic fundamental diagram, especially with the accompanying time plot of vehicle dynamics, we notice that some states are represented unproportionally in the microscopic fundamental diagram. For example, the descending portion after C4 in the time plot, which is here, constitutes only a brief part of the black curve. But it is rendered as a long curve denoted as deceleration in the flow density subplot. Similarly, the brief green curve before C3, which is here, C3, shows up as the long curve acceleration in the flow density relationship, which is this part. For another example, the crest of the black curve is exaggerated as the big finger in the speed spacing subplot, which is this part. In comparison, the speed flow subplot tends to emphasize conditions around capacity. For example, the F F part, this part of the magenta curve, as well as the portion before and after C1, which is this part, are best illustrated here. So FF is illustrated here, and C1 is here. So they are more easily to see than in the time development. Therefore, the flow density subplot is sensitive to small spacing, which helps differentiate high density conditions. The flow speed subplot highlights areas around capacity conditions. The speed spacing subplot enhances states with larger spacing. And the speed density subplot attenuates nothing. Thus, the implication is that when examining conventional fundamental diagram, and in particular fitting equilibrium models, one needs to bear in mind that speed flow density relationship, speed flow and flow density subplots are frequently the bearer of bad news, i.e., they are more sensitive to different choices of parameter values and are able to highlight the differences between models and field data. In contrast, speed spacing and speed density subplots typically tell the good news, i.e., they tend to downplay the above differences. Equilibrium models are functions fitted to the data cloud, which is meant to capture the equilibrium relationship among flow, speed, and density. Therefore, it matters which data points are included in the fitting. A condition is considered as equilibrium if its time derivative is 0. Though there are studies to screen out non-equilibrium data, it is difficult to ensure the result, considering traffic dynamics and raw data aggregation. What we often encounter is a data cloud mixed with non-equilibrium data to which equilibrium models are fitted. By using a curve to represent a data cloud, equilibrium models are oversimplified representation of the conventional fundamental diagram. The left/upper branch, the left and upper branches of the model might make some sense since the data cloud in this region is quite concentrated. However, the right and bottom branch is a wild guess, considering the scattering of data. Errors are inevitable when using this part of the curve to solve traffic problems, such as the applications of LWR model. Conflicting objectives. To qualify for an equilibrium model, each data point on the curve should serve as the equilibrium position, such that when traffic is disturbed, its state will return to the position like the spring mass system. This requires that the curve pass through the center of the data like the green curves. Right? These green curves. In doing so, the curve fails to indicate the correct capacity condition, which is the reasonable maximum of flow. Therefore, equilibrium and capacity are the two objectives that are unable to reconcile in the equilibrium model. To be meaningful by indicating a clear trend, conventional fundamental diagram should feature a strong relationship between speed and density. Such a requirement is roughly met on highways, where drivers mainly determine their speed based on car following distance. This is to say that speed can be considered as a single variable function of spacing. However, the environment becomes more complicated on streets. when car following distance is not the only factor affecting drivers. Other factors such as signs, signals, pedestrians, directions, roadside settings may also come into play. Therefore, speed is a multivariable function of these factors, with the spacing being the only one of them. Therefore, when presenting in the form of fundamental diagram, highway data are more likely to exhibit a clear trend, while in contrast, the street data are typically a mess. Considering that equilibrium models is an oversimplified representation of the data cloud, it is barely acceptable for freeway basic segments, but a far stretch when applied to urban streets. Consequently, it becomes questionable when applying LWR model to address intersection problems, applications of which is not uncommon in the literature. This is because LWR model implicitly assumes that the underlying fundamental diagram suggests a strong equilibrium model, which probably exists on highways, but hardly on urban streets. And therefore, solutions derived from LWR model for urban streets are questionable. Microscopic fundamental diagram and its underlying models can be a solution to the above limitations. For example, the data cloud in the background is a conventional fundamental diagram. The black dotted curve is the equilibrium model generated from macroscopic version of longitudinal control model, LCM model. And the complicated blue curve is a microscopic fundamental diagram generated from the microscopic version of LCM. Obviously, the complicated blue curve is a much better representation of the conventional fundamental diagram than the black dotted curve. When using microscopic fundamental diagram to represent a conventional fundamental diagram, the need to distinguish and eliminate non-equilibrium data points diminishes. Compared with the equilibrium models whose equilibrium requirement is in conflict with the capacity requirement, the microscopic fundamental diagram is able to indicate the capacity condition while sketching out the details of the data cloud. Generated from car following models, the microscopic fundamental diagram reveals what happens behind the scene, while in comparison, equilibrium models are only fit the result of the data rather than offering the reasons behind the data. Now let's turn our attention to some traffic phenomena and their relationship to fundamental diagram. Many traffic phenomena observed in the field are strongly related to fundamental diagram, which has inspired schools of thought to decipher these phenomena. Below are a few examples. Asymmetric behavior. For a given speed and spacing, the spacing is larger during acceleration than during deceleration, i.e., the speed spacing curve loops in a counterclockwise direction with a 2-gem spacing. Traffic hysteresis. The delayed recovery in speed and density cause a figure 8, implying different speeds at the same density level. Capacity drop and reversed lambda. These two traffic phenomena are closely related and typically go hand in hand. More specifically, they take the form of multiple peaks in flow with different capacities, resulting in reversed lambda shape in a flow density relationship. Asymmetric behavior. Newell attributed the phenomenon to non-zero reaction time that cause excess gap to be dissipated before deceleration. Forbes' consideration of human factors regarding perception reaction time appears to explain the phenomena as well. In addition, de Ganzo's two-pipe theory is also relevant. Empirical observations of car following show that the asymmetric behavior phenomenon is the natural outcome when a vehicle decelerates to a stop behind the vehicle in front and starts moving again after the latter departs, without resorting to external assumptions such as excess gap or different reaction times or two pipes. The asymmetry can also be achieved as the natural result of a driving process. Both in reality, drivers do not need to purposely maintain the excess gap or switch to different reaction time, and in theory, using the same model and same parameter values. More specifically, rather than stipulating different driving behaviors, vehicle motion resulted from unchanged driving behavior is able to automatically produce the asymmetry. Many researchers believe that the cause of traffic hysteresis can be described as: one, vehicle traffic operation operates in multiple phases, such as acceleration, deceleration, and coasting. Two, different phases develop along different curves in the fundamental diagram. And three, traffic hysteresis occurs when phase transition takes place. For example, phase jumping from one curve to another. Four, phase transitions are typically associated with altered driver characteristics. For example, different reaction times and aggressiveness and behavior, attaining or dissipating excess gap. Empirical observations of car following show that the stipulation of a phase appears artificial and presumed phase curves violate causality. In fact, the leading vehicle plays a critical role in traffic hysteresis. For example, in a deceleration process, the leading vehicle typically travels slower than eagle vehicle, causing the corresponding point G in the time-space subplot to deviate toward the left. Now, while the situation reverses in the acceleration process, the effect of a loop is exaggerated in the flow density subplot in this part. So, though true near the James Basin L, which is here, a deceleration curve does not necessarily always fly above the acceleration curve, as confirmed by other part of the two curves. So this part, the green curve is under the black curve, but here the green curve goes above the black curve. Though harmless, the assumption of excess gap and altered driving behavior appear unnecessary, since the little psychological evidence is found to either support nor negate them. Fortunately, traffic hysteresis can be naturally resulted both in the field and in theory without these assumptions. Capacity drop and reversed lambda flow density relationship has long been recognized as a twin phenomenon, though their interpretations vary. Causes of these phenomena can be discontinuity between free flow region and congested region, bottlenecks, lane changing events, emerging area where slow drivers limiting fast drivers, asymmetric behavior, and strong equilibrium and acceleration-deceleration phases. A few tentative theories are presented here, illustrating how they portray this capacity drop and reverse the lambda phenomenon. Without necessarily conflicting with the above views, this figure reveals the four capacity candidates in a deeper sense. Candidate C1 occurs during the magenta car following process at the 178th second in the data. Candidate C2 takes place during the blue car following process with a lower speed at the 114th second, C2, which is represented here. And C3 represents the turning point from an acceleration process to a deceleration process on the green curve, C3, and represented here. And C4 is the highest point of the black curve. So which is here. It is difficult to show in the figure because the point is mixed within the curves. This point belongs to the black curve that appear at this time during a deceleration process. Note that C1 and C2 are resulted during car following process, roughly steady states, while C3 and C4 are obtained during acceleration and deceleration process. Those are transient states. Given the existence of multiple capacity candidates, capacity drop is naturally resulted when putting together the data observed during different processes. The microscopic basis of the phenomena typically becomes obscure when these data points mingle and lose connection. In addition, a reversed lambda shape of the flow density relationship can be observed when applying an upper envelope to the multi-curved detail revealing microscopic fundamental diagram. Depending on driver characteristics, especially aggressiveness, vehicle motion dynamics, and particularly how often traffic sensors capture these capacity candidates, the relative positions and magnitude of these candidates may change, different combinations of which may give rise to different flow density relationships, such as skewed parabola, triangular, and reversed lambda flow density relationship. Field theory is an approach to mimic drivers' control of vehicles by representing everything in the driving environment, including roadways, vehicles, traffic control devices, as fields perceived by ego driver, whose control strategy is to navigate through the field among the valley. Longitudinal control model, LCM, is an instantiation of the field theory by only considering vehicles' motion in the longitudinal direction. The equation representing driver's longitudinal control is presented here, with the second equation calculating the desired spacing from the vehicle in front. A simulation based on LCM is conducted on a single lane where vehicle I starts from standing still at the origin and vehicle J in front is also at still, but 1 kilometer downstream. The motion of vehicle J is predetermined, while the motion of vehicle I is governed by LCM model in response to vehicle J. The simulation lasts 5 minutes. The time development of vehicle I's position, speed, and acceleration is plotted on the bottom left. And the corresponding microscopic fundamental diagram is plotted on the bottom right. Note that vehicle I undergoes a series of driving processes, including accelerating, decelerating, following, oscillating, stopping, which are color-coded in the figure so that it is easy to identify what happens behind each segment of the fundamental diagram. By the way, details of this work and much of the talk today are derived from a TRB paper, which has been awarded a TRB 2021 Best Theoretical Paper on Traffic Flow Theory. As indicated in the enlarged speed spacing subplot, asymmetric behavior is the natural outcome of driving processes that decelerates to a stop, the red curve, and starts moving again, the blue curve. So these two, following different paths. Note that the curves are generated using the same model with the same set of parameter values, implying that vehicle motion dynamics alone is able to automatically produce the asymmetric behavior without involving any additional assumptions. Analytically, the asymmetry is resulted when the tangent of the curve dx dot over ds at a jam spacing taking different slopes. And this derivative dx dot over ds is a function of acceleration, the absolute value of acceleration, and their change is plotted here. So as the acceleration becomes large, the difference of the two derivatives becomes more obvious, and thus give rise to the separation of the curves near the jam spacing, resulting in asymmetric behavior. Both single and multiple loops are observed and can be replicated using the same model, LCM, with the same set of parameter values, without having to stipulate different models or parameter values for different phases. In this example, the figure 8 is formed by the blue curve and red curve, and another figure 8 by the blue curve and magenta curve, though the two figure 8s overlap at the right end. Compared with the conventional views, our results of both empirical data and modeling offer complementary but different perspectives. Traffic hysteresis is the natural result of vehicle motion dynamics during which drivers do not need to intentionally assume different characteristics, such as reaction time and aggressiveness, and driving behavior, for example, attaining or dissipating excess gap. In addition, those assumptions might not be the cause, but instead the dispensable effect of natural driving processes. For example, a hysteresis loop may ensue when a driver follows a decelerating leader who changes mind and speeds up, or the situation reverses if the leader does the opposite. The figure shows that the simulated run provides 3 capacity candidates. 1, the highest point of the CN curve as a result of a car following process. 2, the top of the blue curve, achieved when ego vehicle decelerates to catch up its leader. And 3, the top of the magenta curve, obtained when ego vehicle decelerates behind a distant leader. Not necessarily conflicting with conventional views, our results show that capacity drop occurs because multiple capacity candidates manifest themselves when suitable driving processes take place. Noticeably, bottlenecks, merge areas, lane changing events are venues where these processes are more likely to take place. However, capacity candidates can go beyond these venues as long as these processes occur. Therefore, the real cause of capacity drop appears to be these specific processes, while those venues happens to be the right trigger. A reverse lambda shape is sketched out in the figure by the CN and red curves as a result of a car following processes followed by a deceleration process. The conventional view on reversed lambda of flow density relationship is a discontinuity between free flow regime and congested regime. Unfortunately, this view lacks microscopic basis because 1, neither the left branch is necessarily free flow regime, nor the right congested. For example, the left branch can be a mix of the true free flow region, which is the green part, the initial part of deceleration, which is the magenta part, final part of deceleration, which is the blue part, and car following states, which is the cyan part. While the right branch mainly consists of decelerating, which is the blue, and accelerating, which is the blue, and decelerating, which is the red states. 2, microscopically, all state transition take place smoothly without discontinuity. Therefore, if a conventional fundamental diagram were microscopically sound, there won't be a discontinuity unless the states that bridge the discontinuity were not captured. 3, the reversed lambda shape is typically resulted as car following states being the left branch and the deceleration being the right branch, like this part. Remarkably, driver aggressiveness plays a critical role in shaping the flow density relationship. Skewed parabola typically found in outer lanes, often traveled by conservative drivers. Triangle shape in the middle lane, or aggregating all lanes, which is characterized by normal drivers, and reversed lambda in the inner lanes traveled by aggressive drivers. This is exactly the interpretation implied by LCM model and its aggressiveness parameter gamma. All right, I'm going to stop here, and just in case there's any questions from the audience. Thank you very much for your attention.
Thank you so much for your interesting and insightful presentation. Especially congratulations for the best paper award. So now the floor is open to the audience. Please unmute yourself to cast a question, or feel free to leave it in the chat box also. We will read it out for you.
So hi, Daiheng. Thank you for your presentation. Really interesting. As always, you always bring a fresh perspective to our field, and that's appreciated.
Thanks.
My question is, so in the Lagrangian approach that you mentioned, so especially the relationship with the general method to measure traffic variables, which we call EDI's method, right? The generalized definitions of flow and density. So I'm wondering if those definitions will still apply in the case of Lagrangian. So in other words, because you compare the conventional and the Lagrangian, right? Mm-hmm. But there's another one that might be in between, which is EDI's definitions, which, as the way we teach it in traffic flow, they give kind of the true values of the traffic variables. So I was wondering the relationship with this Lagrangian approach.
Yeah, so EDI's method relies on the enclosed region and then calculate the total time spent by all vehicles in the region and total distance traveled by all vehicles in the region to calculate the flow, speed, and density. So it relies on Lagrangian observation of the traffic data, i.e. the vehicle trajectories. But it calculates the flow, speed, density, which are more geared toward the Eulerian description.
Exactly. So yeah, so I'm wondering if it's somewhere in between, right?
Yeah, exactly. Somewhere in between. Right. It's hard to say it's purely Lagrangian or purely Eulerian.
Exactly. So it might be useful or interesting to compare those type of measurements also.
Right. Yeah. Very good comment. Yeah.
Thank you very much.
Hello, Professor Lee, thank you very much for the presentation. I'm Ramchandra Rao from IIT Delhi.
Hi, nice to meet you.
I like the way in which you have related. Yeah, I like the way you have made the common ground for the different kinds of phenomena representing by different symbols. I have one quick comment on the aggressiveness, conservative drivers and the normal drivers. Do these states really exist discretely, or they have a transition smoothly? Because the data what we collected over here, we kind of found that those three states generally are not so much in discrete sense. They would be smooth transitions for all these kinds of drivers. Rather, they'll be following some kinds of distributions. What's your comment on that? Yeah, this one.
Yeah. So the aggressiveness is an attribute to drivers, like perception reaction time. So different drivers have different aggressiveness and different perception reaction time. And therefore, if you focus on a single driver and monitor so that driver's behavior will exhibit a certain kind of translate to a certain kind of flow density shape. And if you model another one, so from my study, if let's look at here. So if the gamma is greater than 0, that means the driver is a conservative type. And if you use a gamma value of this kind to generate the flow density relationship, it is more like a skewed parabola. But if you make the gamma negative and use this value to generate the curve, it will be more likely to be a reversed lambda.
Yeah, thank you, Professor Lee.
Yeah, but of course, we recognize that gamma is a moving target. It varies for individual drivers. So for a person, at some point, some period of time, this driver may behave aggressively, but at some other times, the driver may behave conservatively or normal. Right? Not sure if I answer your question.
Yeah, thank you. Thank you very much.
Are there any more questions from audience? Actually, I have one question for you. In the section of the interpretation, I was curious about the asymmetric behavior that resulting in the hysteresis on density and speed relationship. While I can clearly see that the lambda and hysteresis in the flow density relationship, but I cannot see the hysteresis in the speed density curve that you plotted empirically and also in the simulation part. So in what part of the empirical microscopic fundamental diagram, how can we determine the point of the hysteresis in the speed density relationship?
Okay, so the traffic hysteresis typically takes place in the fundamental diagram as a figure 8. So one part of the figure goes above the other. So in flow density relationship, it's this part. So if you look at the relative height of the black curve and the green curve, so it forms a figure 8 here. But here, this part is too small, so I amplified this part. You will see clearly that the deceleration process goes this path and acceleration goes this path. So it forms a figure 8. And here, it's still quite small, but obviously we can see that there's a loop, right? Actually 2 loops, a figure 8 between black curve and the green curve and here.
Actually, I saw the point of the speed density hysteresis that divides the conventional plot with the free flow regime and the congested regime. Can you show the hysteresis plot?
In a speed density relationship.
Yeah.
Okay. So the black curve indicates a deceleration process. The vehicle following the leader to a stop, and then as the leader starts move, the following vehicle moves as well. So following the leader, and therefore the hysteresis loop is formed in this area by the two curves. So the green curve indicates the acceleration process, and the black curve indicates the deceleration process. So it's obviously this is a deceleration process immediately followed by an acceleration process, just like a vehicle following a driver to stop at a red light, and then when green light comes, the leading vehicle departs, and then the following vehicle catches up.
Okay. Oh, I got it. Thank you for your answers.
All right.
Are there any more questions from audience? So if you have no more questions, so I think it's good time to end today's webinar. Again, thank you so much, Dr. Nee, for being with us today. Thank you to all.
Thank you for having me.
Yeah. And also, we thank you to all the participants joining us. We look forward to see you again in the following webinars. The next webinar is ACC series, and it will be on next Friday at the same time of today, presented by Dr. Rui Jiang. Wish all you have a nice weekend, and thank you again.
All right.
Thank you, Daiheng, very much. Thank you, Gary Young, for taking over. Really nice job.
Thank you.
See you all next time.
Thanks. Have a great weekend, everybody.
You too.
Thank you. Goodbye.
Thank you.